Hi everybody, this is Dr. Bricker here with a review for Exam 3. So if I were to study for Exam 3, what I would do is go over this practice test, which you are doing right now. So homework 9 and 10 cover material from this test. So really from the last week 5 and week 6. Maybe go back through the PowerPoints if you have time, and also read the chapters. If you can't read the entire chapter, take a look at the summaries. Lots of chapters and varied material, but we don't cover every section of all the chapters. So just to refresh your memory, 8.1 through 8.3, so this is balancing forces and torques. 14.1 through 14.4, which is simple harmonic motion, mass oscillating on a spring. So we did not do pendulums, we did mass on a spring. 15.1 and 15.2, kind of an introduction to standing waves. 16.1 to 16.3, standing waves on a string, like a guitar string, piano string, that sort of thing. 13.1 through 13.5, this is the fluids chapter. Again, we didn't do the entirety of chapter 13, but first 5 sections. And then 12.1 to 12.3 plus 12.5, so a little bit of thermodynamics thrown in there. The ideal gas law, specific heat, that sort of thing. So this is the order that we went through material in the class. So it jumps around a little bit, 8 to 14, up to 16, down to 13. But that's the order that we approach the material in class. Okay, practice test looks a lot like the actual test. 12 questions, multiple choice. But the key is, you have to show work. You can't just write down like the final line of your work, and you won't get full credit for that, as you know. Okay, if I were also going to be taking the test, I would make a little sheet of formulas, practice, example problems, things like that. So you have some material ready to go for the test. You give 2 hours to do it, which is kind of a lot of time, but still, get organized before the test. Okay, let's look at the actual test then. Okay, the deepest part of the Pacific Ocean is 11,033 meters, so that's the deepest part, 11,033 meters. Mariana Trench, what is the gauge pressure in the water at this point? The density of seawater, we're assuming, or we're not assuming, it's given to us, 1,025 kilograms per cubic meter. We want to get the pressure down there at 11,000 meters. So here's my picture of the ocean. This is the depth here. Okay, so we've got a formula for pressure at depth. Call that one pressure 2. Here's the pressure at the top. So pressure at the bottom is equal to the pressure at the top, which is usually atmospheric pressure, plus rho g times y. This part here is the gauge pressure. So when you have like a tire gauge, like right now if you took your tire gauge, you went outside to measure your tire pressure, before you hooked it up it would be 0, even though it's exposed to the atmosphere. So that already takes into account the atmosphere. So gauge pressure is like the additional part in addition to atmospheric pressure. So this is the gauge pressure part. And then we have everything here. We have the densities given, G and Y. Try to fit it in down here. So this is the Y part actually. Meters, G's 9.8, and then the density given in the problem, 1,025 kilograms per cubic meter. Okay, so as far as the units go, we have a kilogram meter per second squared. That's a Newton. One of these meters cancel out, so this is newtons per square meter, and a Newton per square meter is a Pascal. So as you see here, pascals, that is a Newton per square meter. Okay, so it's going to come out in SI units. That's what a Pascal is actually. Grab my calculator. So 1025 times 9.8 times 11,033, 1.1 times 10 to the 8th. Okay, good. Excellent. So you definitely see some sort of pressure at depth sort of problem. All right, let's look at the next one here. In a flask, 166 grams. Okay, so be careful. So 0.166 kilograms of water is heated using a 64 watts of power. Okay, so the power, 64 watts. Now don't forget the use of the unit watts. It's a joule per second. With perfect efficiency. Okay, how long will it take? So how much time does it take to raise the temperature from 15 to 25? Okay, so this is in Celsius. And then the final temperature is 25 degrees Celsius. So the change in temperature, T final minus T initial, will be equal to 10 degrees Celsius. Now remember, that as far as the increment of temperature goes, if you change the temperature by 1 degree Celsius, you also change it by 1 Kelvin. So this would be equivalent to raising it by 10 Kelvin. Okay. All right, very good. We know the specific heat is given for water, 40186 joules per kilogram Kelvin. This is also equal to joules per kilogram degrees Celsius if you wanted to look at it like that. So if you think about it, we're going from 15 to 25. How much heat is required to raise the temperature of this much water by 10 degrees Celsius, or 10 Kelvin? We can figure out how much heat or energy is required to raise the temperature. We know the rate that we can supply energy, so we can figure out the amount of time. So let's do that first. Let's figure out the amount of heat. Q, M, C, delta T. So the mass, 0.166 kilograms. We got 4186 joules per kilogram Kelvin. And now the change in temperature is 10 Kelvin. Okay, let's look at the units again. Kilograms cancel out, Kelvin cancels out. So this is how much joules are required. 0.166 times 4186 times 10. Okay, so 6.94 times 10 to the third joules. Heat, energy, you notice the units are joules. Okay, so this is how much is required. We can supply 64 joules per second, so we can figure out the amount of time. So remember, the power is the heat divided by the time. So I'll do a little bit of algebra. The amount of time then is the heat divided by the power. Okay, good. 6.94 times 10 to the third joules, and we supply 64 joules per second. So this will tell you how many seconds. Okay, good. So I still have that on my calculator, divided by 64. So about 108 seconds. Okay, so round it up to 110. Okay, good. So you'll see some sort of problem with, this idea of specific heat. Okay? All right, good. Next one, we have a mass, 0.25 kilograms, stone, attached to an ideal spring. Now, we do have a lot of varied topics for this test, which might seem more difficult, but actually, in my opinion, it's not, because if it's a mass attached to a spring, you know exactly what that's from. That's the simple harmonic motion section. So hopefully on your notes that you prepare, you'll have a little simple harmonic motion section. Okay, so you wouldn't try to do like buoyant force with this problem or anything, right? It's a mass on a spring. It narrows it down what you can use. Anyway, going back to the problem, simple harmonic motion with the period of 0.64 seconds. What is the force constant? Okay. The beauty of simple harmonic motion is that once you identify it as simple harmonic motion, here's the relationship between period, mass, and spring constant. Okay? So the period is 2 pi square root of m over k. So if you notice, the amplitude's not in this formula. The period just depends on the mass and the spring constant. Not kinetic energy, spring constant. Okay? So here we're given the mass, we're given the period, and we want to measure the spring constant. We have everything here. You have to square both sides. Don't forget to square the 4 and the pi. M over K. So then K turns out to be 4 pi squared M over the period squared. Now this might look a little strange as far as the units go, because we have a mass, which is kilograms, period, which is seconds squared. How is that a Newton per meter? Well, if you multiply the top and bottom by meter, you can do that. It's like multiplying by 1. This turns out to be a Newton per meter. So the units do work out. So just put the numbers in here. I guess the only other thing to really say about this is the frequency is 1 over the period as well. Okay, so this would be a very hard problem to do with just trying to use kinematics or something like that, because the force is not constant. The more the spring stretches and compresses, the force changes. Luckily, we have this in our physics tool belt. Okay, next one. If a wave has a speed of 362 meters per second and a period, the amount of time, 4.17 milliseconds, so times 10 to the minus 30 minus 3 seconds. What's the wavelength? Okay, so the wave speed is the wavelength times the frequency. It's also the wavelength divided by the period. You know why is that exactly? Let's just look at a wave. So the wavelength is this distance. So the amount of time it takes this crest to go from here to here is called the period, right? The amount of time to go from here to here is the period. So the speed then is the distance, which is the wavelength, divided by the period. Oops, couldn't see that part. So the distance, wavelength, divided by the amount of time it takes for that to happen, the period, and you get the speed. And then we know that the frequency is 1 over the period, so you could write it like that if you want to. Okay, so this part and this part we can use. So the speed times the period will give you the wavelength. Okay, kind of an intro problem with waves. Okay, very nice. Okay, so this comes from chapter 12. The absolute temperature of an ideal gas is directly proportional to which of the following quantities? So the answer here is the average kinetic energy of the molecules. So this is the relationship we have between the kinetic energy of a gas and the temperature. So the temperature really is just a measurement of the kinetic energy. As you can see here, for one molecule, the average kinetic energy is 3/2 Boltzmann's constant, that's what the Kb is, times the temperature, and this is measured in Kelvin. So the bigger the temperature, the more kinetic energy the gas has. The total thermal energy is, take the amount of particles you have, remember that's what big N is, the amount of particles, and multiply it by the energy of one molecule, and you get the total thermal energy. Okay? So you'll see something similar to this question, actually, one of these explain ones. As far as explain goes, I could just write this and say, kinetic energy proportional to temperature, just from this. Okay, so number 6 here comes from chapter 8. An athlete holds a 7.5 kilogram shot put in his hand with his lower arm horizontal, as you can see here. Okay, his lower arm has a mass of 2.8 kilograms, and its center of gravity is 12 centimeters from the elbow. Okay, so the shot put is way down here, and the center of gravity of the actual arm itself is given as 12 centimeters from the elbow joint. So from here, 12 centimeters over, maybe somewhere like here, would be the center of gravity of his actual arm. How much force must the extensor muscle, which is marked F sub m, exert on the lower arm? Okay, so when you're holding your arm up like this, you got the weight of the shot put here, the weight of the arm itself here, these torques would make it rotate clockwise. The torque provided by this muscle here, this extensor muscle, would make it rotate the other way. And so the torques are balanced about this pivot point. So let me draw a little picture of kind of like this. So here's the pivot point. We have force muscle here. The weight of the arm itself is here. And then the weight of the shot put is acting here. It's really the normal force onto the arm from the shot put, but it's the same. They're equal to each other, so I just wrote it like this. Now I did not draw these to scale. This force is way bigger than the other forces. We know some distances. This is 0.12 meters. This distance all the way to the shot put is given as 30 centimeters, so 0.3 meters. And then this little distance here, I'll have to write it like that so we can see it, 0.025 meters. So why don't I call this distance to muscle? This one could be distance to arm, and again, you can call these whatever you want to. This one could be distance to shot put. That's what the R means. It means distance. Okay. So again, as far as torques go, this and this are making it rotate this way about the pivot point. The muscle is making it rotate this way. Okay, so the torque by the muscle making it go one direction has to be equal to the torque from the arm plus the torque from the shot put. Okay, there's also a force here from the joint itself going this direction, but we don't have to consider that because that is the pivot point. So there's no torque if the force is right at the pivot point, right? So you can't just balance, you can't just do this problem with forces because there also is a force here, you know, this direction. But we don't need to consider that one because we're looking at the torques about that point. Okay, good. So then we'll have to put in the numbers here. Force from muscle times distance to muscle is equal to, you know, because torque is force times distance, this would be the weight of the arm, that's the force, and then the distance to the, where the force is acting, and then plus the weight of the shot put, and then the distance to the shot put. Then the only thing that you don't know is the thing that you're looking for, this. So you do a little bit of algebra, well, maybe just one step of algebra really. Weight of arm, distance to arm, weight of shot put, distance to shot put, divided by the distance over to the where the muscle's acting. So you'll definitely see one of these balancing torques problems. I highly recommend going back and looking at homework 9. We had a problem with the deltoid muscle, so take a look back at that one from homework 9. Okay, hint. All right, halfway done. Next one, also a fluids problem, so chapter 13. Water, which can be treated as an ideal and incompressible fluid, flows at 12 meters per second in a horizontal pipe with a pressure of 3 times 10 to the 4th. Now, if the pipe widens to twice its original radius, what is the pressure in the wider section? Okay, so we go from a narrower section to a wider section. The narrower section, we know that the speed, I'll just call this V1, is 12 meters per second, and P1 is equal to 3 times 10 to the 4th. Pascals, good, SI units. Now, over here where it's twice as big, there's a speed, and there's also a pressure here. And that's what we're trying to figure out. Okay, so a couple things going on here. We can get V2 pretty easily. This is a Bernoulli fluid flow problem. There's also another component, like if this pipe were going to raise up to a different height, we might have to consider that, but this is a horizontal pipe, so we don't. Okay, so we got P1, P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. And again, this is a horizontal pipe, so we don't have the height component of Bernoulli's. Okay, so and we're trying to figure out P2. So we got to do a little bit of algebra here. P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared is equal to P2. Okay, we don't have V2 yet, but we can get it. So the pipe goes from this size to twice its original length. So imagine you're trying to water your garden and you've got your finger over part of the opening here, and what if you take your finger off and you make the area wider? The water comes out slower. So it's going to be coming out slower here, right? It's the same amount of water, but it's a bigger diameter here, so the water is going to actually slow down. So it's a volume flow rate problem to get V2. Okay, this is perfectly good, but we need to get V2. Okay, so I know that V1 times area 1, this would be area 1, is equal to V2 times area 2. Now it's a circle, so I can say that this is V1 times pi R1 squared is equal to V2 times pi R2 squared. The pi's actually cancel out. Okay, so V2 then, just solving for V2. V2 is equal to V1 R1 squared over R2 squared. Okay, I'm kind of doing this in a rigorous mathematical way. You could just say the radius is twice as big, so the speed is 1/4 as much. That you can do that as well, and you'll see why in just a second. So this would be 12 meters per second R1 divided by 2 times R1, right? Because that's what R2 is. Don't forget to square each of these. I'll do it like that. And then you see it's 1/4 as much. So 3 meters per second, right? Because R2 is equal to twice R1. That's what they tell you in the problem. Or you could reason it that if the radius is twice as big, the speed is going to be 1/4 as much, because the speed is proportional to the distances squared, as you can see here. Okay, so now you have this amount, and you can take this and put it in for V2. I didn't really leave enough room on this one, actually, it looks like. So if you had to use the back or something, that would be fine. Okay, so then you can solve for P2. Just put all your numbers in. Okay. Pascals, that's the SI unit. You're perfectly good there. We've got the speed in meters per second, so this will come out in pascals then. Okay, very good. Okay, next one. This is a chapter 16 type problem. A string with linear mass density, kind of like a little bit with 15 as well. Okay, linear mass density, that's mu. Be careful with the units. 1.5 times 10 to the minus third kilograms per meter. It's under a tension, I'm going to call it force of tension, of 20 newtons. What should the length, what should be its length? So how much is the length if the fundamental frequency is 220 hertz? Okay. Now when they say fundamental frequency, that the mode is 1. Not the mass, but the mode of 1. Okay, so what do I know about standing waves? Well, I know that the speed is equal to the square root of the tension divided by the mass per length. It's also equal to the frequency times the wavelength. Now the wavelength for standing waves is also 2L over m. Now don't forget, this m is mode, not mass. Okay, it can be kind of confusing. This is mass per length, this is mode. Okay, and we're trying to figure out the length. Okay, excellent. So when you tune a guitar string or a piano string, what you're doing is changing the tension. If you change the tension, you change the frequency. Now the wavelength is whatever the wavelength is. It's 2L over m. It's determined by physically what you have there, but it's the frequency that changes when you change the actual tuning by changing the tension. Okay, so there's a few ways of approaching this. Let's take a look at this. You know, look, we have the mass per length, we've got the tension, we've got the frequency. My eye jumps to this equation, this part of it here. So let me square both sides, and you get tension divided by mass per length is frequency squared times the wavelength squared. Okay, so I can solve for the wavelength. Maybe I didn't even need to square it, actually. I mean, this is perfectly good. If you have this on your formula sheet, that would be fine. But if I can get the wavelength, which I can, because I know the tension, the mass per length, and the frequency. If I can get the wavelength, that's good, and then I could use this equation to get the length. Okay, so this is good, but I didn't even need to actually square it. Okay, so the tension divided by the mass per length, both of those are under the radical. Divide that by the frequency is equal to the wavelength. Okay, maybe I'll put the numbers in on this one. Okay, so the tension, 20 newtons, mass per length 1.5 times 10 to the minus third kilograms per meter. That's under the radical. And then 1 over the frequency. And the frequency was given as 220 hertz. That's equal to the wavelength. Okay, so let me do it like this. I'll just do 20 divided by 1.5 EE minus 3. Now I'm going to raise that to the 1/2 power. That's the same thing as taking the square root of it. Divide by 220. So the wavelength turns out to be 0.524 meters. Okay, that's not, as you can see, that would have been tricky if that was one of the answers here, right? Because your eye might just jump to that. But to get the actual length from this equation, the wavelength divided by 2 is the actual length. The mode was 1, so I didn't even bother to write that. Okay, so 0.524 meters divided by 2 is the wavelength. So that's about 0.26 or so. Okay. Okay, so you'll definitely see a problem, similar to this. These, standing wave on a string type problem. Okay. Simple harmonic motion. When is the speed the greatest? Let me draw a little picture of a spring. So pretend there's a mass on a spring. This is its relaxed length. You take it and you stretch it out here and you let it go. This is something called the amplitude. Okay. When you're at this point, this is when all of the energy is kinetic, spring potential energy. So kinetic energy is 0 because it has to stop there. This is when the spring potential energy is a maximum. This is when the speed is 0. The amplitude of the acceleration is a maximum. And then you also have the point over here where the spring is compressed. So this would be x is equal to 0. Okay, this is also the amplitude. Same thing happens over here. Kinetic energy is 0. Speed is 0. Spring potential energy is a maximum. At this point, when x is equal to 0, this is when the speed is a maximum, the acceleration is 0, kinetic energy is a maximum, and spring potential energy is equal to 0. It's not stretched or compressed. Okay, so let's go back to this question though. In simple harmonic motion, when is the speed the greatest? The speed is the greatest when you pass through equilibrium. So the speed is the greatest when x is equal to 0, acceleration is 0. Let's see if we can, that's right here. That's where the speed is a maximum. When the acceleration is 0, okay, so far I think that's good. When the potential energy is a maximum, okay, that's not true. This is where the potential energy is actually 0. When the displacement's a maximum, well, that's not true. This is when the displacement is 0. When the magnitude of the acceleration is a maximum, okay, that's not true either. That's these endpoints. Okay, so as far as explain goes, this picture would help out. Or if you wanted to do it in words, you could say something like, the speed is the greatest when the mass passes through the equilibrium position. The equilibrium position corresponds to the acceleration being 0. There is no spring force at that position, right? It's not stretched, nor is it compressed. Okay, so you'll definitely see one of these explain type problems. Now you can't just circle the answer and don't say anything. You'll get 0 points even if it's correct. You have to explain. It doesn't have to be a lengthy explanation. It can be, Just a sentence or two, or a formula, something like that. Okay, another standing wave problem. Oscillating with a frequency of 950 hertz. What is the speed? Okay, the length is 0.6 meters. Now, that's not the wavelength, that's the actual length. The wavelength is 2L over M, and M is the mode. What's the mode of this? Count the amount of high spots here, the antinodes. 1, 2, 3. M is equal to 3, so you can get the wavelength. So why do I want the wavelength? Well, the speed is the frequency times the wavelength. So the frequency is given, I just have to get the wavelength. So 2 times 0.6 divided by 3. So it looks like 0.4 meters. Frequency of 950 hertz. A hertz is a 1 over a second, so 1 over seconds times 0.4 meters. 950 times 0.4, 380 is the wave speed. Okay, good. That's one of the answers there. Excellent. All right, just a couple more problems to go. Just verify that we did that one correctly. Number 10 was D. Okay, good. Okay, so this is from the fluids chapter. You'll definitely see a buoyant force one there. So from the fluids chapter, so far we've had pressure at depth. You'll see one of those. Bernoulli's equation. You'll see one of those, and I gave you a hint. It's also going to be a horizontal pipe. We actually had to use the continuity idea as well to get V2 in that problem, but we'll see something like that, and then you'll see a buoyant force problem. Okay, what buoyant force, how much is the buoyant force? In other words, does a 60 kilogram gold crown, or sorry, 0.6 kilograms. Yeah, 60 would be a lot. Experience when it's immersed in water. The density of gold is 19.3 times 10 to the third kilograms per cubic meter. The density of water is 1,000. So we just want the buoyant force. Okay, so here's the formula for the buoyant force. So it's the density of the fluid times G times the volume of the fluid that is displaced. So if this crown is completely submerged, then the volume that's submerged is the total volume of the crown. It's equal to the volume of the fluid that's displaced. So if you put like a certain volume in a fluid and it's submerged, the water level goes up by the same amount. So the volume of the fluid that's displaced is equal to the volume of the object when it's completely submerged. Okay, so density of the fluid's given. G is just 9.8. We need the volume of the fluid that's displaced. Again, that's the same thing as the volume of the object in this case. So the density of the gold is going to be equal to the mass of the gold divided by the volume of the gold. Remember, that's how density works, mass over volume. Okay, so then we can get this. The volume of the gold, the crown, is the mass of the gold divided by the density of the gold. And that's, as I said, going to be the same thing as the volume of the fluid that's displaced. Okay, got my calculator. I don't have room to write the numbers, but I'll just do it on my calculator. So we have 0.6, that's the mass of the gold crown, divided by the density of gold, 19.3 EE3, so really small. 3.1 times 10 to the minus fifth cubic meters. You'd expect it to be small, right? It's measured in cubic meters. Okay, so the volume of the gold is the same thing as the fluid, volume of the fluid. Okay, so buoyant force, density of the fluid, 1,000. 9.8 meters per second squared. And now here's the volume of the fluid that's displaced, the same thing as the volume of the crown. So 3.1 times 10 to the minus fifth cubic meters. Okay, so I still have that on my calculator. Times 9.8 times 1,000. So pretty small here. 3 times 10 to the minus 2 newtons. And you can see the units would come out in newtons, like this cubic meter and this cubic meter cancels. Kilogram meter per second squared. Turns out to be newtons. Okay, so you'll definitely see something with the buoyant force. So if you've got an object that's submerged in a fluid, you're always going to have this buoyant force. And you can still rely on Newton's laws. You can look at all the different forces acting on an object. So definitely take a look back at those problems on the homework. Homework 10 actually dealt with the buoyant force. Okay, very good. It's actually one of my favorite forces. I think the reason is if you put a beach ball and you submerge it in water and you let it go, it goes flying to the top. That's the buoyant force. It brings back memories of the summer. That's why I think I like it. Okay, now final problem. A car starts out when the air temperature is 288 Kelvin. Okay, initial temperature 288 Kelvin, and the total pressure is okay, the absolute total pressure, that's atmospheric, everything taken into account, starts out with a pressure of 500 kilopascals, so times 10 to the third pascals. After driving a while, the temperature increases to 298. Okay, so this is an ideal gas type problem. If you've had a chemistry class before, you might have done these kind of problems already. What is the pressure in the tires at this point? Assuming the volume does not change. Okay, so again, this is kind of an ideal gas law. PV is equal to, I'll use the physics version of it. Okay, N, Boltzmann's constant, times the temperature. Just make sure the temperature is in Kelvin, which it is. Okay, so what is not changing in this problem? Volume, number of particles, Boltzmann's constant does not change. So I could write this as P over T, moving the T to that side, is equal to particles, Boltzmann's constant, divided by the volume. So when you start out, you have the same amount of particles, Boltzmann's constant, times the volume. That part does not change, right? So I could do it like this. Initial pressure, initial temperature. This has also got to be equal to final pressure, final temperature, right? Because this part is the same thing for the initial situation and the final situation. Okay, so initial pressure, initial temperature, final pressure, final temperature. Okay, and then we can solve for whatever you want. We're looking for final pressure. Okay, initial pressure, TF over TI. That's the final pressure. And then you have everything. Now the pressure has increased a little bit, so the temperature has increased a little bit, so the pressure is going to increase a little bit. So any of these answers has to be bigger than 500. If I had to guess, I would just say it's 507, but you can put the numbers in and actually get that. So you will see an ideal gas law problem on the test. I'm not saying it's initial situation versus final situation. It might just be using something like this. Okay, maybe I'll give you pressure, temperature. You have to figure out the amount of particles, something like that. So, so again, take a look back at the homework, and then be familiar with the ideal gas law. Okay, any questions? Just email me, and I'll talk to you soon. Bye bye.